Hi Miss, I'm Teo Ziyue. My student ID is 0338984. So for this video, I'm going to explain the ordinary differential equation. So what is the differential equation? Differential equation is an equation containing the derivative of one or more dependent variables with respect to one or more independent variables. The derivative is measures of how a function changes as its input change, which we call rate of change. So there are two types of differential equations. The first one is the ordinary differential equations, which contains one or more independent variable with respect to single independent variables. The second one is the partial differential equations, which contains one or more dependent variables with respect to two or more independent variables. So there are three different types of notation for derivatives. The first one is prime notations, the second one is Leibniz notation, and the third one is Newton's dot notation. So there are several types of methods to solve ODEs. The first method is the separation method. So basically this method we just need to separate the equations into two sides where each side will only have the one functions, which means for these equations the left hand side is only got the y function and the right hand side only got the x function. So we integrate it and then solve the equation so we can find the final answer. For the second method, right, the second method is the exact method. So it's for this method, we first need to determine the exact whether the question is exact ODE or not. So if it is exact ODE, we just need to substitute all the variables into this equation. For these equations, we can recall from calculus that if a function uxy has continuous partial derivatives, its differential is du equals to partial u over partial x dx plus partial u partial y dy. So we just integrate the partial over partial x to get the x squared y plus k function in y. Then we derive it again with respect to y. So we can equating it with the partial u over partial y. And we can get the value of k prime y equals to 1. We integrate it, then we can find the ky is equal to y plus a. So we substitute it into equation 1. So the final answer is b equals to y bracket x squared plus 1, where b is equal to c minus a. So this is the non-exact method. For the non-exact method, right, if it is the non-exact method, you just need to multiply both term m function in xy and n function in x and y with another function f called integrating factor. So in order to find the integrating factor, we need to use this formula. So in order to let this formula be exact, the equation will become partial fm over partial y equals to partial fn over partial x. So we notice that the question says let f is equals to fx. So the equation will become this equation. And we substitute all the values into these equations and we can find 2f is equals to negative x df dx, and we use the separate method and integrate it so and solve the equation after, and finally we can find the fx is equal to 1 over x squared, which is the integrating factor. Then we multiply it with both sides into the original equations. Then we realize that it will become the exact ODE. And in order to get the final answer, we just need to use the methods that we already discussed with in the previous slide. So this is the integrating factor method. For this method, if the equation is homogeneous linear ODE, we just we just straight use this general solution for the linear ODE, linear homogeneous ODE, which is CE, which is exponential power of negative integrate px dx. For the non-homogeneous, right, which the Rx is not equal to 0, we need to use the integrating factor as well, which its formula is simply E, which is exponential power of integrate px dx. So here got the example, which is the non-exact ODE. So we just find the integrating factor, which is x power of 4, and then multiply it into the equations. And we notice that the d bracket x power of 4y over dx is, we can get this value by applying the product rule. So we interpret it and solve, and we can get the final answer. So for the last method, right, is the Bernoulli equation. The Bernoulli equation we use to transform nonlinear to linear ODE. So this as for this method example, right, it is a nonlinear ODE. So we set u is equals to y power of 1 minus a, and we get the value of y power of negative 1. And then we differentiate it, and it will become negative x plus y power of negative 1 over x. So we know that u is equals to y power negative 1. We sub into the equations, and we will get a non-homogeneous linear ODE. So to solve these equations, we also need to find the integrating factor, and then we substitute it into the equations, then solve the equation, and we can find the final answer. So now I'm going to discuss the homogeneous linear second order ODE. So this equation is set to a homogeneous linear second order ODE. So in this second order ODE, right, there are three cases. The case one is the two real roots if a squared minus 4b is more than 0. And the case 2 is a real double root if a squared minus 4b is equal to 0. Case 3 is complex conjugate roots if a squared minus 4b is less than 0. So this is the example for case 1, which is two real roots. We can write the original equation into its characteristic equations. For example, this is a lambda square minus lambda minus 2 is equal to 0. So we can find its roots by using this formula, which is 2 and negative 1. So the general solution for the case 1 is y is equal to c1e power of 2x plus c2e power of negative x. So this is the example for case 2, which is a real double root. So we use the same method as the previous slide, but notice that for the case 2, we only have one root. So the general solutions is y equals to bracket c1 plus c2x e power negative 0.5x. So this is the example for case 3, which is complex conjugates. For the complex conjugates, the value for the a squared minus 4b is less than 0. And we have the imaginary roots for this case, which is 3 over 2 plus or minus square root 7 over 2 pi. So the general solution for this case 3 is y is equals to e power of 3 over 2x bracket c1 cos square root 7 over 2x plus c2 sine square root 7 over 2x. So this is our main topic in this video, which is the application in automotive industry. And the application is the car suspension, which is related to the second order ODE and dam system. Many real-life engineering applications use the concept of viscous damping, such as shock absorber on the motorcycle and car suspension. So before we proceed to solve our modeling questions, we need to find the equation of motions. As you can see, a schematic of a mass spring mechanism undergoing viscous damping is shown in diagram 1. Like the spring, the damping force is always opposing the motion of the mass. So a good approximation is damping force is linear proportional to the velocity of the mass. Thus, the damping force is equal to negative c y naught. The y naught is represent the dy dt. And the mass has now two opposing forces, which are F spring is equal to negative ky by Hooke's law. And the second one is the F fluid is equal to negative c y naught. So now we apply the Newton's second law, which is sigma F spring plus F fluid. So we know that F is equal to MA. So the equation 1 will be MA is equal to negative KY negative, sorry. So the equation 1 will be MA equals to minus KY minus CY naught. So we rearrange the equation 1 into a homogeneous linear ODE. Homogeneous linear second order ODE with constant coefficient, which is m y naught naught. Y naught naught is acceleration, as acceleration is total change of velocity, plus cy naught plus ky is equal to 0. So we divide the equations by m, and then we can get the equations 2, which is y naught naught plus c over my naught plus k over my is equal to 0, where m is equal to spring mass, c is damping coefficients, and k is spring constant. So actually, this modeling is referred to case 2, which is critical damp. And that means the value for a squared minus 4b is equal to 0. So these are the we can say initial conditions for these modeling questions. The spring mass is 300 kg, spring constant is 1200 Newton per meter, and the initial displacement is 0.15 meter, and the initial velocity is 0 meter per second. So from the equation 2, which is this equation, we need to find the damping coefficient. So we label A as C over M and B is K over M, and we use the formula of A squared minus 4B equals to 0, as this is case 2. So we can find the value of C is 1200 Newton second per meter. After we find the value of C, we substitute all the values into the equations, and we write it in the characteristic equation, which is lambda squared plus 4 lambda plus 4 is equal to 0. And then we can find its roots, which has only have one root, since this is the case 2, which is negative 2. So the general solution for case 2 is y equals to bracket c1 plus c2t bracket e power of negative 2t. And since the questions have give us the initial condition, so we just sub all the initial condition into the equations, and we can find the particular solution of y function in t equals to bracket 0.15 plus 0.3t e power of negative 2t. So as you can see, the diagram 2 shows the behavior of the suspension system. The car is pretty much returned to its equilibrium positions in less than 4 seconds, which is quite a slow response for most real-world applications, and this case, which is critical damping, is what car manufacturers aim for in most cases. So that's all for the video. Thank you, Miss, for your listening.